All right. Well, yeah, my name is Nick and my partner is Zibin. Today we're going to be presenting on something that extends from paper 4, which has the microfabricated hinges. And here our project is it's a new hinge that is a locking variation, and it can also allow for locking at a specific variable angle. Cool. So what is the purpose of our project? So to take a step back, we talked a lot about surface micromachining throughout the semester, and what that allows is high resolution in the horizontal direction because you're depositing very thin layers and then etching away small amounts. But in the vertical direction, you have pretty low resolution. And so this doesn't make it as ideal for 3D microstructures with a tall aspect ratio. And so what paper 4 introduced was an integrated hinge design. So you add the hinge into the structure, allowing you to rotate the structure out of plane vertically and to kind of unlock that third dimension. And it also brought up the idea of locking your structure once it's assembled vertically. And so what our device does is it similarly locks like this here, but the advantage it has is it's a very low assembly force relative to the amount of force that it can withstand before breaking once it's assembled. And so that gives the potential to use fluidic assembly, which is using water to kind of agitate the structure to assemble it automatically, or like automate the assembly. And so what that can allow you to do is kind of scale up assembly for a variety or a mass amount of these structures.
So the alternatives, Nick was just talking about how we found inspiration from paper 4. So the first alternative is, as you see on this top left, just a regular microfabricated hinge. This isn't self-locking, but it's kind of how we started our design. And you'll notice our design has a similar structure in that it has a base and it has a staple and it has a lift plate. You can see the hot wire anemometer uses another locking structure. Although it's not self-locking, it actually requires manual assembly in order to lift up this plate and then lower this one onto it. And then the tissue growth dynamometer has a similar structure. And then finally, the vertically supported comb resonator has a locking plate that could theoretically be self-locking, but I believe there's a small concern that there's not enough holding force, so it could potentially collapse back down if you were going for a method such as fluidic self-assembly. So the overview, take a second to enjoy this animation because it took a really long time to make. The things we want to point out are the base. So we see the base is these two plates, and then we see the lift plate in pink. The lift plate just has holes in it right now so that you can imagine other things that you would put on it instead. And obviously holes allow it to dissolve the etchant faster. And then on the staple, we have this cantilevered beam, and the cantilevered beam acts as a spring. And this is sort of a locking snap fit. So in high volume consumer electronics, there's a couple types of snap fits. One is self-locking, and then another is like removable. So this one, when it locks in place, it self-locks because the cantilevered beam slips back into place. And you can see there's holes in the bottom base, and we'll go over those later too. But it's just important to note that this tab fits below, and then the staple constrains it from moving up and down, and the cantilevered beam constrains it from moving left and right. So it's fully constrained once it snaps in place. Everyone enjoying that animation, hopefully.
All right, so when designing the cantilevered beam, we have to look at what forces are being acted on it. And so as you're actually lifting up that plate, it's deflecting the beam upwards, and you can simplify that model as like a fixed beam with a force being applied at the tip. And with that, you can develop a relation between the stress felt in the beam compared to the length of the beam, which is this graph shown in right. And so as you increase the length of the beam, that stress goes down, but that also makes the beam more compliant, which is not necessarily what we want, because we do want it to be able to resist force once it's assembled. And so what we've ended up choosing here is 26 micrometers for the beam length, and that guarantees us a factor of safety of 1.5 to the yield strength of the polysilicon. Our structure is also designed for the MUMS process. So it uses a nitride layer, 3 polysilicon layers, and then the 2 sacrificial oxides. And to kind of break down the parts, so the nitride and poly zero form what we call the base. and that has like a cutout in the bottom, which allows the lift plate to kind of pivot off of, and it also supports it once it's fully assembled. And then the poly 1 defines the lift plate, and on that you would add like whatever structure you want on top of this that you want to be lifted up. And then poly 2 defines the staple, which comprises of the cantilever beam element.
So what we showed you earlier in the animation was for a 90-degree locking hinge. This is a theoretical concept for a variable angle hinge. So theoretically, you could go from anywhere from 90 degrees, 89, 87, you could go even lower. And then potentially there is a low angle limit though, and I'll go over that in a minute. But this is just the concept for an angled plate, and we'll also go into some use cases for an angled plate in a second too. But I was mentioning a low angle limit, but first it's important to note just the tolerances in general. So if we look at our normal hinge, literally normal because it's 90 degrees, we can see that if you apply a force to the top of the lift plate shown in blue, it corresponds to a compression force on the cantilever beam. And that works out well because as a cantilever beam, it places it into a failure mode of buckling. And we did some math that we'll go over in a minute, but it's pretty strong in buckling. So this works out very well. And the result of this is an error tolerance that's estimated with this diagram and this equation. And if you calculate the space here left over, so the gap space, it's a result of the mumps process and mask inaccuracies and also just tolerances so that it always works. And we calculated that if you were to go for 90 degrees, you have a tolerance of about plus or minus 4 degrees. And then as I was talking about in the last slide, an issue with having a really low angle. So this is about 45 degrees, and we think that that could work pretty well. But if you go lower, you can see that this blue beam, when a load is applied to it, either fluidic or just a weight on the end of it, it puts the cantilever beam in bending. And now the cantilever beam in bending is sort of designed to be a little bit compliant. And so whatever tolerance you have just from these gaps, you now also have the fact that this beam could potentially move up and down as an issue as well. Does everyone understand that fairly well?
Yes.
All right, awesome.
All right, so to kind of characterize our mechanism, we have 2 key metrics. One is the force required to lift it and assemble it, and then also how much force or torque it's able to withstand once it's assembled. So on this diagram on the left, as you're lifting the lift plate, it's pushing up against the cantilever beam, and that force that the cantilever beam applies, let me just step back. The force required to lift the lift plate, you can see there's a big lever arm relative to where the force that the beam is being deflected. And so that gives you a mechanical advantage, and it really drives the lift force down. So what that comes out to be is 30 micronewtons to lift the beam up. And then looking at how much force or torque the structure is able to withstand once it's assembled, you have to think about what's going to fail first. And so, like Zibin was saying, if you apply load on the lift plate, which is the tall thing sticking up, that's going to create a torque, which is going to be reacted by your cantilever beam, and that's going to put it into compression. And so we're going to see a buckling failure there at some critical load. So that critical load is about like 5,800 micronewtons. And then when backing out how much torque that is on the plate, that's about like 0.043 micronewtons per meter. And that's about equivalent to 430 micronewtons applied at the top of that lift plate.
Hopefully you've enjoyed all of the animations and pictures so far. We just wanted to go over some key specs. So it has a pretty tight angular tolerance when it's placed orthogonally at 90 degrees, and we see that it's around plus or minus 4 degrees. As Nick mentioned, the force to assemble is roughly 30 micronewtons. However, the force to break is around 430 micronewtons. What this means is that we have a large range in fluidic assembly. So if you move it at a certain speed, you have a big tolerance of lifting that plate up before you break it. A concern if you had a low breaking force is that you would lift it and then immediately break it, but we're estimating that this is not the case, and it gives us a good chance of success with fluidic assembly. You can see on the bottom left and right, we see a couple different designs. So you have your normal orthogonal design. This design is probably best suited for 90 degrees, but then we also have a theoretical concept for 45 degrees or any other angle, barring the low angle limit, whatever that would work out to be for your specific process. We thought of a couple use cases. So the first use case is an anemometer, and this would be potentially a new type of anemometer, but actually we would take advantage of that bending cantilevered beam, and any wind or fluid that would be pushed against the beam up here, it's not shown, you can see it in the animation, but any fluidic force that would go across that would bend this cantilevered beam. So if you measured the deflection using some device, you could estimate using just the relationship of the dimensions and the material properties, you could estimate how much force is being applied to that beam. And we also have this idea to use angled mirrors. So there's a couple of different processes where you could potentially have lasers on a small chip. And if you hit a mirror that was angled with the laser, it would shoot it out of plane of the chip. And then you could have it in a usable workspace potentially. So you could create a little laser etching device or something like that. And then fluidic ramp is just an idea of redirecting airflow across the chip. So if you wanted to keep a little area protected, you could redirect the air to go up, or you could slightly shoot it off a ramp. If you had a little free floating chip in like a human cell or something, you could use air brakes that would fold out and slow down your little device. And then, as the professor mentioned earlier in the slides, there's actually several uses that already use out of plane chips. And so basically any of those would also theoretically work on this as well. But given the added benefit of fluidic self-assembly, so that you can potentially do this at a high volume manufacturing. Any questions?
I think you guys did a wonderful job. You set a very good and high bar example for the project presentation. You have an animation to clearly kind of present the concept and how things may work. And you have the analysis, also the operation and example and some calculations. So those are very good. Any question from other student? I have one short question. It looks like you want to etch nitride in your process, but that's not part of the MEMS process.
Yeah, we kind of noticed that when we were writing our report. So we actually have like, if you want to show like a backup slide showing where, yeah, in order to like properly use the MEMS process with this, we would have to only etch the poly 0 and not etch the nitride.
Yeah.
And then you also have to add like some supports underneath the poly 2, which is like the dark blue, to kind of support your cantilever beam during fabrication. Or also get these like weird jogs like in the left picture. But yeah, it's a good catch.
Okay, very good. Any other question from the student? If not, we will have the second